Alright, this video is going to go over the library of functions and the piecewise defined functions. Alright, the first thing we'll go over is what we call the parent linear function. Your book refers to it as the identity function. Alright, it's given by the equation f of x is equal to x, and the domain is all real numbers. Likewise for the range, it's all real numbers. If you notice, it's symmetric about the origin, so the parent linear function is odd. Also, if you notice, it bisects the first and third quadrants. The next function we'll go over is what we call the parent quadratic function. Your book refers to it as the square function. Alright, the equation is just f of x is equal to x squared, hence why they call it the squared function. If you notice, the domain is all real numbers like before. The range is just given by the set of all y values such that y is greater than or equal to 0. And that'd be another squiggly bracket. And if you notice from the graph, it's symmetric about the y-axis, so it's even. So it's an even function. And if you notice about the quadratic, it's decreasing on the negative part of the x-axis, but once it crosses over the y-axis into the positive part, it starts increasing from 0 to infinity. Next function we'll go over is what we call the cubic function. Alright, this is what the graph looks like. If you notice, both the domain and the range would be all real numbers because the x's keep going on and on forever, and so do the y's. And if you notice, since it's symmetric about the origin, it would be odd. If you notice, it's constantly increasing from negative infinity to positive infinity. Alright, the next type of parent function you're going to learn about is what we call the square root function. You notice it's just given by f of x is equal to the square root of x. And the positive square root function gives you the half of a sideways parabola. If you were to do negative square root of x as well, you would have the other part of your sideways parabola. But anyway, what I'm about to tell you about the domain range, this pertains specifically to the positive square root function. So the domain of the positive square root function is just all real numbers, and the range is just the set of all y values such that y is greater than or equal to 0. I don't know why that says negative y, because it shouldn't. But just know that's supposed to be positive y right there, not negative y. But for reason the stupid thing won't allow me to erase right now. So it's just a set of all y values such that positive y is greater than or equal to 0. Alright, the next function we're going to learn about is what we call the cubed root function, the parent cubed root. Alright, the equation for the cubed root function is just f of x equals the cubed root of x. And the domain, in case you can't tell from the graph, would be all real numbers. And the range is also all real numbers. I don't know why I started writing the cubed root function again. The range is all real numbers. And if you also notice, it's symmetric about the origin, which would make it an odd function. And that's supposed to be, you can add the IO in after that in your notes. Alright, the next type of function we'll go over is what we call the reciprocal function. Alright, this is what the graph of the reciprocal function, what the parent reciprocal function looks like. The parent reciprocal function is just f of x equals 1 over x. You notice the domain is all reals, except that, you notice if you plug in 0 for x, you get undefined, so it's the set of all real numbers except that x cannot equal 0. If you notice for the y values as well, for the range, y can never equal 0 either, because there's a horizontal asymptote where y is 0, so the range would be all reals except that y cannot equal 0. Since it's symmetric about the origin, this would be an odd function. Alright, the next function we're going to talk about is what we call the absolute value function. The parent absolute value function is just f of x equal to, and then it has the x with two inside, vertical bars, and the graph looks like a V shape. Now the domain of the absolute value function, since it keeps going off to both the left and right, the domain would be all real numbers. And the range is just everything above the point. So it'd be the set of all y values such that y is greater than or equal to 0. And since it's symmetric about the y-axis, it's an even function. Alright, the last type of parent function we're going to go over is what we call the greatest integer function. This is what the greatest integer function looks like. And the notation, we use a couple of different notations for this. Alright, and the domain and range for the parent greatest, well, before we get into the domain and range, I want to show you the notation that we use. There are two different ways we do the notation. The first one is just f of x equals int of x. Another way we write the notation is just f of x equals, then the variable x in brackets. And you hear my son in the background trying to say hi. And my daughter too. Alright, and the domain of the greatest integer function, in case you couldn't tell for the graph, it would be the set of all real numbers. And I'll bring the graph back down for a minute to show you. Alright, if you notice, it's defined for every value of x, even whenever you have the circles. All you have to do is step up, and it's defined for that same value of x. So, it is defined at the open circles after you step up to the next step, if you will. So that's why the domain is all real numbers. And in its range, if you notice, it's not the range only exists for the set of integers. It doesn't exist for any decimals or fractions or irrational numbers. So the symbol for integers is just a script Z, like that. This is like a letter Z, but with another line, like that. Alright, now we'll go over what a piecewise defined function is. It's when a function is defined by different equations for different parts of its domain. We're going to go over an example to kind of illustrate that. Alright, here's an example. It says the function f is defined as... Alright, there's f of x. It's equal to negative 2x plus 1 on the interval from negative 3x is less than or equal to x is less than 1. And it's equal to 2 when x is equal to 1. And when x is greater than 1, f of x is equal to x squared. See how for different parts of the domain it's defined by different equations? That's what a piecewise defined function is. Alright, and the part A is find f of negative 2, f of 1, and f of positive 2. So f of negative 2. Negative 2 is contained in the first interval, the one from negative 3 to positive 1. So you plug negative 2 into the first equation, negative 2x plus 1. So it'd be negative 2 times, instead of times x, would be times negative 2 again plus 1. That equals 5. F of 1. Now it says when x is equal to 1, the function is equal to 2. And positive 2 is contained in the third interval, the one for x squared. So you plug it into x squared, which means it'd be equal to 4. Now for part B, it says determine the domain of f. If you notice, it's defined for any x value greater than or equal to 3. So for part B, you could say the domain is a set of all x values such that x is greater than or equal to 3. Another way you could write the domain is just the interval, a closed bracket from -3 since x can be equal to -3, and since it keeps going on past there, it'd go to infinity and it'd be a parenthesis. You could write it both ways. Now for part, yeah, that's right. Alright, look, it says locate, alright, for part C it says locate any intercepts. Alright, when it says locate any intercepts, you have to check for both x-intercepts and y-intercepts. Now for y-intercepts, you need to take each of the three parts, then minus 2x plus 1, the 2, and then the x squared, and set them all equal to 0. Because remember, for y-intercepts, actually that would actually be for x-intercepts, rather, sorry. Remember, for x-intercepts, the y-coordinates are equal to 0, so that's why you set them equal to 0. So, hold on. So for the first equation, when you said the minus 2x plus 1 is equal to 0, you get that there would be an x-intercept at 1/2. Since 1/2 is in that interval from -3 to +1, there is an x-intercept at 1/2, 0. And since for the second equation, 2 can never be equal to 0, there's no x-intercept there. And from here, there would be an x. For the third equation, there would technically be an x-intercept where x is equal to 0. However, since 0 is not in this part of the domain, we disclude that as well. So the only x-intercept is at 1/2, 0. Now for the y-intercept, you plug in 0 for x. And since x is contained in the first, since 0 is contained in the first interval from -3 to 1, you plug it into -2x plus 1, and you get that there's a y-intercept at the point 0, 1. Alright, for part D, where it says graph f. Alright, here'd be a picture of the graph. If you notice, this linear part here is the minus 2x plus 1 from -3 to 1. This little dot right here, the point 1, 2, that's the second part. It's where the function is equal to 2 and x is equal to 1. And this curved looking part, that's the x squared, ranging from 1 onward. You have to graph each part separately. Now determining the range, it looks like there are no y values past -1. But that's an open circle. So I'd say the range would be the set of all y values such that, since it's an open circle, that'd have to be greater than -1. And for part F, it asks if it's continuous. If you notice on the graph, let me pull it back here. See if I can, not that part, the picture. If you notice, when x is equal to 1, you have what's called a jump discontinuity from here to here. And plus, it's defined at an entirely different point for x equals 1. So for that reason, it is not continuous.